Okay, so this will be the last topic for us for chapter 1, and I will divide this into two parts. So the first part will be this video, then the second part will be later on. Because you already familiarize yourself with the vectors. How do we write a vector and the formats, the unit vectors, and also how to we also discuss the different coordinate systems that we will be using in EE126. So now we can go to another topic, the vector calculus, which is also the same importance with the first topics for us to understand more the concept of electromagnetism. So the first thing that we will be talking is, because this is vector calculus, we look at the differential elements. The first one is the differential volume. Differential volume element. So when we say differential in calculus, you already know the concept, understand the concept of differentials or derivatives. Derivatives means when you take the change in x, change in y, when delta x approaches zero. That's the definition of a uh, derivative. It means this is a very, very small quantity. So if I say differential volume element, then this is a volume that is very, very small. So you take a piece out of a whole volume that is very, very small. So if we plot this one in our coordinate system. So first, let us look at the differential volume in rectangular coordinate system. Rectangular coordinates. So when we take a differential volume, the shape of that differential volume, because the lengths of the sides of that volume will become very, very small because we're taking the derivative. It approaches zero. So what happens is those lines become straight lines. Those curved lines become straight lines. So if we take a differential volume, uh, we can just look at a a cube with the sides, or rectangular prism with sides and the different coordinates. So let's say this is all right, the cube, or the rectangular prism with the different sides. Or so what are the sides of this rectangular prism? So it depends on the direction, or the direction of that sides. So this is z, this is x, and this is y. So this length here, it's in parallel with the y-axis. So we can say that is uh, with respect to y, but it's a very, very small length. So that will be the differential length dy. And this one here, this is in parallel with the x-axis. So this will be our dx. And of course, the one that goes up, or the height of the rectangular prism, that will be our dz, because it is in parallel with the z-axis. So this is our differential volume. This volume here, this rectangular prism here. And from geometry, we already know how to solve for the volume of a rectangular prism. And to do that, that's just equal to length times width times height. Our length is dy, dx, and width is dx, and the height is dz. So therefore, the differential volume now, dv, in rectangular coordinate system is just equal to the product of the sides. So this is just dx, dy, and dz. So this will be our formula for the differential volume in rectangular coordinate system. How about in cylindrical coordinates? In cylindrical coordinates, it's not true that the volume, differential volume is also equal to, because here in rectangular we have x, y, z coordinates. In cylindrical coordinate system, we have rho, we have rho, we have p, and we have z. So if you want to determine the volume, is it d rho, d phi, dz? This is not true. This is not correct, because if you look at the graph, or if we graph again our differential volume in cylindrical coordinates. So if this is the cylinder, you take a differential volume from this one. What we do is we just take a very small prism from here. This will be the differential volume, this rectangular prism here. So now, what are the sides of this rectangular prism? So we have, obviously, the first one is this side, and because this is raw, and that length should be our d raw. Then for this side, it's the same. It's in parallel with the z-axis, so that's just our dz. But for this side here, it's the same as this side here. That is not equal to d phi, because this is d phi. This is the very small change in the angle phi, and that length. This is length. This is the length of the side. So d phi is not a length. D phi is an angle. So if we want to determine the length, so if we draw the top view of that one, so this is our differential volume. This here, our differential volume, the top view of our differential volume. This is our d raw, because this is raw. This is raw from here to here, and that is d raw. And what we want to determine is this side. What should be this side if this is an angle d phi? So from, again, analytic geometry or geometry, when we want to determine the arc length, this is arc length. So if you have an arc length, a simple arc length, if this is theta and this is r, if you want to solve this arc length s, it's just equal to r times theta, where theta should be always in radian, because that's an angle. It should be in radian. So if you look at a circle, if you rotate that, the angle of that should be, or the theta should be equal to 2 pi, because one revolution. And if you solve for the arc length, then the arc length is just equal to the side, or the radius r, times the angle 2 pi. So this is s equals to pi r, and this is actually the circumference of a circle, because that's the arc length of the whole revolution, one revolution. And that's how we calculate the arc length. So here we also apply that concept. This side now here is just equal to the radius, which is rho, and you multiply it with the angle, so rho d phi. The angle is just d phi. So this side now here is this rho d phi. So if we solve for the differential volume in cylindrical coordinate system, we just multiply again the sides, because that's the formula for the volume, length times 3 times height. We have d, or rho d phi, or you can just rearrange this to d rho, then multiply it with d phi. D rho is fine because this is length, and also dz is fine because that's also a length. So this will be our formula for the differential volume in cylindrical coordinates. So there's a factor here that is rho. In rectangular, it's just the differentials. While here we have another factor rho. So don't forget that rho. And for spherical coordinates, coordinates, what is the differential volume? Coordinate system. So again, we need to draw draw the sphere, visualize our volume, differential volume. So if this is our sphere, let's just draw this. Then we take a very small volume from here. Let's just slice this one. This is like a watermelon. When you buy a watermelon, you want a pre-taste. Then you just take a hole somewhere here. And if we project this one to the origin, then we have our differential volume here. This will be our differential volume. Then what are the sides of this differential volume? The first one that we can determine is this side, somewhere here, this one here, because this is R, this is radius here. So this side here is just equal to dr. And for the other sides, next is this side here. So if we cut this one, this is the z axis. If we cut that, if this is our cross-sectional view of that sphere, this is z axis, and this will be our xy plane. And somewhere here is our volume, and this is the cross-sectional view. So this is our volume here, cross-sectional view of the volume. And we already know this one. This side is dr because this length from here to here is rho or r. That's the radius of the sphere. And next is, how about this side? How do we determine this side? We need to know the angle. What is this angle? We know that this angle here from z-axis, that is our theta, angle theta from the z-axis to the radius. So this is a very small angle, so this will be our d theta. So if we solve for this, is again the arc length. Our formula is just the radius multiplied by the angle, which is the theta. So this is just r times d theta. So we already have two sides. For the last side, this is the last side here. So how can we determine that side? We cannot just multiply r with the angle. We know the angle here. This is, if you project that, this is our phi. So this angle here should be d phi. D phi. But we cannot project that here because if we solve this length here, we can draw just like in cylindrical, that one, and that angle, this angle here, this is actually d phi. That's the projection of dp at the top side, and this will be our length. And if we take out that the top view of that, it will be look like this one. This will be our top view of the volume. This is dr, and this is what we want. We know that this is d phi, but the problem is this side here is not equal to r. This is that side. This side here is the same as that side, and it's not equal to r. We can just call it capital R. But we can solve that by using this triangle here and that one. So if we write that triangle, this will be r, small r, and this angle is this angle somewhere here. And that is just equal to, that is the angle from the z-axis. That is our theta. This angle is theta because this is the z-axis. And this is r, capital R. That is what we want to solve. And to solve that, r now, and that will be equal to that are using this hypotenuse and that angle, so opposite, so that will be sine. So if you take the sine of theta will be just equal to the opposite side, which is r, all over the hypotenuse, small r. So that r will be equal to r sine of theta. This is our side or our radius here. And if you know that radius already, which is r sine theta, we know the angle d phi, then we can now solve for this side. This side is just the product of the radius, and this is r d phi. But r is r sine theta, so this is just r sine theta d phi. So if we collect all, so this is side is r sine theta d phi. Collect all the sides now. We can determine the volume. Differential volume is just equal to the product of those sides. We have dr, we have r d theta, and we have r sine theta d theta. And that will be r times r, so that's squared. Then we have sine theta. Then the differentials. Let's start with dr, then we have d theta, then we have d phi. So this will be the formula for the differential volume in spherical coordinates. So we derive the different differential volumes in different coordinate system. So after differential volume, we can determine the other differential elements. We have the differential surface areas. Differential areas. So in rectangular, they are just all rectangles. And if you want to determine the area of a rectangle, it's just length times width. Rectangular. So in rectangular coordinates, that differential area is just equal to, there are different areas here. We have, if you want this, if you have a cube, let's just draw this. So if this is our differential volume, and this is dz, this is dx, and this is dy. So if I want to determine this area is just the product dz and dy. So we can say the differential area, the magnitude, because we can later on we can represent area in terms of vectors. This differential area is just equal to dx or dy times dz. So if we make them a vector, let's just make them a vector, so that we can determine what differential area are we solving. So here, the differential area, the direction of the differential area in electromagnetics, we just take the perpendicular vector, unit vector, to that differential area. So for example, dy times dz, which is this one, so the direction will be in this direction, which is the unit vector ax. So we just multiply that with ax. The other one, another differential area in terms of vector. So if you want this one, this is dz times dx, but the direction will be in this direction. That's a y, because this is y, x, and z. So dA in that side will be equal to dx times dz in dy direction. So we are just using these directions to represent what area are we solving, because there are different areas here. And if you want to solve the area at the other side, that's just negative ay. Also for ax at the back, it's just negative ax. And for the one that goes up, this area, the unit vector will be going upward, and because that's perpendicular to that area, this will be az. And that differential area now will be equal to, that's dy times dx, or dx dy. It's just length times width in the z direction. Az. So these are our differential area in vector form. We can also make them in scalar by removing these unit vectors. This is in rectangular coordinates. In cylindrical, In cylindrical, it's all the same again, but instead of using dy, dz, we will be using in terms of here d raw, d phi, and dz. Those are the sides. So if you want to determine this area is just equal to d raw multiplied by dz, and we can put again our direction into that direction, which is going through a phi direction. So we can write that here. I'll just copy this in here. Then we can write our formula for dA. The red one, so let's change this one. dA will be equal to, or what are the sides? We have d raw multiplied by dz, and this is in the p direction. So it's just the cross-sectional area of the cylinder. For the area that going outward, the surface area, you can change color. This area here, the direction will be in this direction. This will be the direction of raw. So if we solve that differential area, that is just equal to what are the sides? dz, and this side is raw d phi. So raw d phi times dz. This is in the raw direction. And lastly, for the one that goes up, this area, so the direction is in this direction. This is az. So dA, the vector form will be equal to d rho and rho d phi. Rho d phi times d rho. Rho d rho times d phi. Times d phi. This is in the z direction. So these are our differential area in cylindrical. And lastly, for how about in spherical coordinates? Spherical coordinates. So for spherical, let's copy this one. Or I just draw it again. So let's try to draw the sphere again here. Then we already know the different sides of the differential volume. So this is our differential volume somewhere here. So first, this area, we can shade it. This is the first area. And the direction will be in this direction. That is AR direction, going outward. So if we solve that area, differential A, that blue one, that is just equal to this length here. We know this length already. And we also know this length. So from here, we have this length is dr, and we have rd theta. Our dr is that one, or we have r sine theta d phi and r d theta. This one is r d theta, and this one is r sine theta d phi. While our dr will be this side here. This is dr. So now for that blue area, that is just equal to rd theta times r sine d phi. So r times r is r squared, and we have sine theta, and we have d theta d phi. For the other differential areas, just like this one, it will be in that direction. There should be a phi direction, positive a phi. That area, dA now, it will be equal to what are the lengths? dr, and we have this one, rd theta. So dr times rd theta. So this is r dr d theta in the phi direction. And lastly, for this one, let's try another color. This area here at the bottom. So this will be in this direction, which is the A theta direction. And the area will be dr times this one, r sine theta. So dA will be equal to dr times r sine theta. R sine theta dr times d phi in the theta direction. So these are the different differential areas in the different coordinates. You can later on, if you want to solve for the magnitude only, you can disregard the directions. Usually that's what we do, but I put here directions. The first one, I forget to put direction for this. The blue one is AR direction. I just put direction to identify what area are we solving because they're not equal. And they have different formulas for the different areas. Next, we have volume, we have areas. Then lastly, also for the differential lengths. You also need to know the differential length in the different coordinates. Length system. First, in rectangular coordinates, we have, if you look at the rectangular, this one is just a rectangle. I just draw the cube, zoom in for the differential volume so that we know what's the differential length. The differential length will be the length of the diagonal. So from this point up to this point. So that is our differential length, dl. We can also make them again a vector by putting our unit vectors because this is in x, y, and z. So this is our ax. This is or ay. This is ay. Ay, ax, and ez. So if we write the vectors now, we can just make it in the x direction. We have ax. In the y direction, we have ay, and for the z direction, we have az. So this is in vector form. If you want to determine the actual length, it's the magnitude of dl, just dl. This is just equal to the square root of dx square plus dy square plus dz squared. So for the magnitude, this is the formula. For the vector, we have the unit vector for the different directions. So this is in rectangular, the differential length in rectangular. In cylindrical, cylindrical coordinates, what will be our dl? So let's draw the rectangular prism again. Let's just zoom in. It's the same, it's the diagonal. The differential length is the diagonal. But this time, because the sides are different, so here, you can, from here to here, that's our differential length, dl. So if we solve that, that's the diagonal of the cube. But first, we need to know the lengths of the sides, length, width, and height of this rectangular prism. We already solved that here. For cylindrical, we have d rho, we have dz, and we have rho d phi. So this will be d rho here. This will be dz, and this will be rho d phi. So if these are our x, y, and z, length, width, and height. If you want to solve for the diagonal is just equal to the square root of the length squared plus the width squared plus the height squared. So here, if you solve the magnitude of the differential length, this is just equal to the square root of those sides. We have d rho squared. We have rho d phi squared. Then we have dz squared. That's the differential length, the magnitude of the differential length. Now, if we include the direction, then you just multiply it by a rho, a phi, and az. Okay, so we can just take this one. And lastly, for the spherical coordinates, in spherical coordinates, the differential length, if we draw this rectangular prism again, then we have the sides of this rectangular prism. In spherical coordinates, we have r d theta, we have r sine theta, and we have dr. So let's say this is our dr. This is dr. This is, what's that? We can make it that as our r sine theta. R sine theta d phi. And this one to be the other side, r d theta. So the diagonal again is this diagonal here. That's our dl. So if we solve for that length, differential length is just equal to the square root of the sides. We have dr squared plus r uh, r sine theta d phi squared, then plus r, or we can rearrange this. We first write r d theta squared plus r sine theta d phi squared. So this will be the differential length in spherical coordinates. So if you know the sides of the rectangular prism, basically you can derive all the formulas for the volume, the area, and also the length. So that's just the basic pattern, because we just use the different formulas in geometry to determine this length, differential length, volume, and area, such as length times width times height, length times width. And for the differential length is just equal to the square root of the diagonal, or the diagonal of the rectangular prism. So this is the first part, the different elements, differential elements in the different coordinates.